Good afternoon, good evening, good morning, wherever you are. We are on the eighth lecture. In the last lecture, we talked about metals in water. And that essentially is to tell you how water sources are increasingly getting contaminated and what those risks are. Today, we get into something even more specific and closer home. That is the issue of arsenic contamination. And I'm going to discuss this subject not necessarily as arsenic in water, but arsenic in the environment. Because arsenic can be in air, it can be in water, it can be in food, it can be in soil, it can be everywhere, and all of those can affect us. But then it is closer to us in terms of its impact through water, so it will have greater relevance to water. The discussion will be more about arsenic in the environment. And when we talk about such a subject, obviously history comes in, its chemistry comes in, its biochemistry comes in, its civil engineering comes in, its public health impacts come in. And all of these in the past nearly about 50 years have attracted the interest of a lot of people. Ever since a classic paper in Nature, which said that arsenic is the largest mass poisoning in the history of humanity. This was a study that came from Bangladesh. So ever since that, there have been lots of studies. And it is one of the major environmental issues that has been investigated extensively across the world, and that program is continuing. So therefore, as you can imagine, there's a whole lot of data that exists. And if you start thinking or looking at today's data, papers keep coming, almost several papers a day. So therefore, it is difficult to cover this subject area in its comprehensive fashion in one lecture. So therefore, I will point out to something, largely the important aspects, and then direct you, those who are interested in, to read something more, and for which we will give you some additional reading material. I have also written extensively about it. There are several reviews. Several of my students have written PhD theses on it. So all of these exist. I'll briefly mention those, and you can read about it. This lecture content itself is written more in a textual fashion, so that description or descriptive fashion will allow you to go through this in more detail at leisure. I'm not going to read each one of those lines, as it may take time. We will also have some time for questions. Having said this, if you look at arsenic in the environment, a lot of people have used arsenic in different ways. You might have heard about its use as a poison. Of course, it has been used as a slow poison, slow killer across civilizations. In the past nearly 1,000 years, the written history exists about use of arsenic for about 800 years or so as a poison. But arsenic has also been used for many useful purposes, as you see in this great picture of Vincent van Gogh. So Van Gogh, just before his death in 1890, as you know, 1889, this is one of his celebrated uh, self-portraits. The green that you see here, the shades of green that you see here, is because of an arsenic pigment. And that pigment is Paris green. Paris green is copper acetate triarsenite, having this formula that you see. And it has been called by various names. And across continents, people have used it for many applications. In India, those of you who are older might recall teak wood electric poles, which are faintly in green color. And that grain is because of this pigment, because it is also an insecticide. Later on, of course, it was also used as a rodenticide and many others. It was also used in medicine to cure certain diseases. But over the past nearly 115 years, arsenic and its toxicity to humans through water, that became a subject of study. So this subject of arsenic in water, arsenic in the environment, and its impact is not very new. That's the essential message that I wanted to tell you. This got intensified after that great paper in Nature. As I was telling you, arsenic, the mass poisoning in the history of humanity. But before that, this was used also as a poison in many parts of the world, including in the context of Napoleon Bonaparte. This mineral is coming from arsenic, right? This arsenic as an element is in the periodic table, as you know. Arsenic in its form that is used is a mineral form, and that is there everywhere. In fact, over 200 different arsenic minerals exist. And if you start thinking about arsenic in tiny quantities, there are thousands of minerals which can have arsenic. So if you go to British Museum, here close to this place, you see plenty of arsenic minerals. But that mineral is across the planet, widely distributed. It is a metalloid. So it is, as you can see, this is distinguishing between the metals and the non-metals. So this is a metalloid, as you know. And this exists in nature in the form of oxides. So it exists as As2O3. But this As2O3 as a solid, it is safe. It exists in nature, and it does not get into water significantly because it is not present on the surface. It is present in the interior. But if it contacts with water, it forms various species. The species in this context, when I am referring to, it's like iron can exist as iron 3+ and iron 2+ species. So these are two distinct chemical entities. So even this Fe2+ or Fe3+ can exist in different hydroxides, oxychlorides. So different kinds of ways that exist in nature, in water, they are called species. So arsenic oxide, when it interacts with water, it forms species such as arsenic acid. Arsenic acid is As with OH 3 times. So it is written as H3AsO3. So this is a soluble form of arsenic, which is called an arsenic species. Now, there can be other soluble forms of arsenic, and they form other species. Now, although this is a common oxide of arsenic, there is another oxide of arsenic, which is arsenic 5 oxide, that is As2O5, similar to phosphorus oxide, phosphorus pentoxide. This also dissolves in water. It gives you different species. So there are many arsenic species that can exist in water. We will soon see that the solubility depends on number of parameters, including pH, ionic strength, temperature, and several others. So as a result, many arsenic species exist in water. That's the sum and substance of the story. This arsenic oxide is soluble in water. So this trioxide has a large solubility, 1.2 grams at 0 degrees centigrade, going all the way to 5.6 grams at 75 degrees centigrade. So it's highly soluble, which means that if there is that oxide in presence of water, that water can be contaminated. But over the years, many, many years, people have not been consuming that water just because that water is deep under the earth. So it is not present as, it is not surface water. So it's groundwater. And therefore it has not been used. Now, with civilization, with our industrial activities, we have ways to dig deep and explore water, exploit water, extract water. So as you extract water from depth of that kind, obviously arsenic can come into our daily activities. So this is the essential aspect of arsenic. But as you dig deeper into specific regions of the planet where there is this oxide or other forms of oxide present, now it comes into our daily activities, and that associated impacts occur. Now, there are several other finer details which I am not going to discuss. For example, this arsenic oxide itself exists in different kinds of crystalline forms. Different polymorphs exist. Their solubilities are different. All of these. But those of you who are interested in it can read further. That information is available on this slide. This very same kind of methodology I have used for other slides as well. There's more content on this, but I will not be spending time on this. Now, imagine that you have some species such as this, H3ASO3. Now, this H3ASO3 can, as I told you before, it is AS OH 3 times. One of these H can go away, and the O can be in the minus form. So that is this species. But one more H can go away, it can give you this. Or one more H can go away, it can give you this. So which means this particular molecular form has 3 different kinds of species. They can coexist in the environment. So when they coexist in the environment, obviously they can be taken up by an organism. All the 4, one of them, many of them, all these are possible. Their concentrations can be different in water. One can be more, one other can be less. And the biochemical impact can be different. One can be complexing with DNA, another need not. One can interact with sugars, another need not. All of these complexities exist. So now that we know more about the toxicity, we know each one of these species and their impact in greater detail. So over the years, the past 50, 60 years, lots of understanding has happened as to the biochemistry of this versus that versus the others. So this is about arsenic in its 3+ form. Now, it can also be arsenic in some other form, right? As I just told you, arsenic in 5+ form. That also gives you additional other species and their appropriate biochemistry. So therefore, this soup of arsenic then gets complex. Because of that complexity and lots of studies that exist, it is difficult to go into each one of these in this lecture in detail. We have also books on this, and I have been contributing to this area. So a lot more can be said, but we will keep that. We will not get that discussion into this class today. Because arsenic is present in the environment, and that has been a toxin that is known, there have been global interests. So UNICEF then went on to study which are of those wells in West Bangladesh which contain arsenic. So they classified the bore wells into bore wells which are unusable with a red mark and bore wells which are usable by a green mark. So this started somewhere around 1998. So after the Bangladesh government ruled in 1993 onwards that there is official declaration of arsenic contamination, widespread arsenic contamination, UNICEF, along with the government of West Bangladesh, went on to label several of the pumps. Similar activities happened in India also. So this is one such labeled pump. Obviously, it helped a number of people from avoiding unsafe pumps and using safer pumps for their water needs. Lots of such studies have happened. Now, arsenic, I told you, can exist as different species. So this is the arsenic that is present, let us say. So this is arsenic in its 5+ form. It interacts with water. It gives you one species like this. But it happens at a pKa of this. So this guy can become this one at another pKa. This can become this at another pKa. So as you can see, there are pH-dependent controls on the species that you have in water. Think about arsenic-3. Similar kinds of things exist. Now, what it means is that depending upon the kind of conditions, right now we have talked about water, just water and the proton. That's all that is there. But water can have many things, right? Chloride, bromide, nitrate, many things. Depending on all of those, that is called the hydrochemistry. Lots of different kinds of controls can be there that determine the concentration of these species. So they exist in water. That's the essential summary of this. But it is not that this is the only thing that exists in water. These are the inorganic arsenic species that exist in water. So in the earlier slide, you might have seen I-arsenic. So this classification means that many of the species that one refers to is inorganic arsenic. But as it interacts with atmosphere, species in the atmosphere, species in water, species in soil, and in the body, it can give you new species. So imagine this entity, this entity, this arsenic, instead of the OH that is present, imagine this is arsenic. These are methyl groups. So you get some species such as these. So this is arsenic, ethyl 3, CH2, COO minus. So this is arsenobutane. So this is an arsenic containing molecule that is present largely in marine environment. So fish contain this. Also exists in us because of the chemistry that happens. The good thing is that this is non-toxic or reduced toxicity because it can be excreted. This is another kind of species. It's similar to, this is called arsenocholine. It's similar in structure to glycine, for example. So it is similar to a biomolecule. It's similar to an amino acid. So which means that it can be transported in the biological system. This is another one. This is dimethyl arsenic acid. There are different such species. Now, several of them, as I said, all of these fellows are organic and they can be excreted. But another important aspect is that they're all with methyl groups or some hydrocarbon species, which means that they can be dissolved in tissues. So it is possible that our body, not only our body, all living bodies can have these kinds of entities. Now, the way in which they react or the concentration of these depend upon pH, as we talked about. There are two kinds of diagrams that it is important to know. One is the concentration versus pH diagram. This diagram that you see is a very important diagram in environmental science. Imagine you start from a species here called H3AS5O4. This is an arsenic 5 species. This is the concentration that is present in water, let us say, or all the species are in this form. Increase the pH slightly, its concentration goes down, following the pKa equation that I told you before. And what happens is that this species becomes this species. One H goes out. And its concentration increases, and it decreases with increasing pH. And the next fellow comes up, which is another proton goes out from here. Its concentration increases and decreases. So this way, one can be systematically converted to the other. So this is about arsenic 5. What about arsenic 3? We start with this entity. Its concentration decreases after some pH. Now, another species comes up and its concentration decreases, etc. But what is of interest to us in drinking water is a pH window of 6.5 to 7.5. So if you take that window of 6.5 to 7.5, this pH window, you can have species, which is one of this guy, which is HAS5O4 minus, and this species, which is H3ASO3, and another species, which is HASO4 minus, coexisting. Essentially, these three species can exist in solution. So our interest is, or interest in water chemistry or drinking water chemistry is to see how much of each one of these species exist and what is their impact on health. Now, this is one side of the story. There's another very important diagram, which is due to this person called Pourbaix. This diagram is called Pourbaix diagram. Pourbaix was also not only a chemist, he was also a pianist. Died, well, very recently, 1998. Pourbaix diagram is part of every water chemistry textbook. So in the context of arsenic, this diagram is essentially to say how different species coexist or convert from one to the other, depending upon the electrochemical potential EH and pH. So looking at this diagram, at low pH and high EH, essentially the condition is highly oxidizing. You get arsenic 5. And lower conditions, of course, you can have reducing environment. One species can go to the other just by change of EH and pH. So depending upon our electrochemical conditions, our pH conditions, it is possible to predict the concentration of the species. So this is essentially the summary of this. Now, there are further more details in it. We will not discuss each one of those details here. Now, this is also dependent upon temperature. As you know, Nernst equation, there is pH and temperature comes in predicting the electrochemical potential. So obviously, all of these are related. Now, Pourbaix, by himself, he was studying corrosion. So over many years of his life, he looked at the properties of metals under various conditions. And these properties are today useful in understanding corrosion in every environment. Now, we talked about different kinds of species in water, particularly around the pH of interest to us in drinking water. In these conditions, different oxidation states exist. And the toxicity of each one of these species is also different. Arsenic 3 is more toxic than pentavalent arsenic. Yesterday in the class, last class, we saw that chromium 3 is less toxic and chromium 6 is more toxic. Here, arsenic 3 is more toxic than arsenic 5. And we also saw that inorganic arsenic is more toxic, organic arsenic is less toxic. Now, arsenic, how it is transported in the environment, it's called the mobility of arsenic. So this depends upon multiple factors. It depends upon redox potential, pH. It also depends upon the biological activity, adsorption of a given species on surfaces and all. To what extent arsenic 3 can be adsorbed in nature in comparison to arsenic 5 will decide how much of the species, a given species, would exist in water. So all of these are important in discussing impact. How do you know a given species is present in water? One way to do this is by what is called speciation. Speciation, you saw a diagram, but how do you know how much of that species is existing? There are two methods often used. One method is a method called Raman spectroscopy, looking at the vibrational frequencies of a given species. You can estimate what is the concentration of the species. The other way of doing this is by a technique called ion chromatography. So in the laboratory, we do that experiment also. So how much is there is known. How much of total arsenic is there is also known by another method, which is typically using elemental analysis. There are multiple forms of elemental analysis, but you can estimate the total elemental form. Then you can estimate the total different chemical forms. So by doing this, we understand what is in the environment and what impacts the environment. Now, if you study this concentration, different regions of the planet contain different amounts of arsenic. So in India, we measure up to this much, or people have measured in India up to about 500 ppb of arsenic is measured, meaning 500 microgram per liter. Most regions, which is arsenic contaminated regions, have arsenic concentration below 200 parts per billion. Now, so that's at the highest extreme of arsenic contamination. When you say typical arsenic contamination, we are talking about below 100 ppb. Many places have very less arsenic concentration, and typical arsenic concentration in arsenic-free regions is below 1 ppb. So on the surface soil, in Chennai, for example, if you measure arsenic concentration, it is less than 1 ppb. So it is not toxic at all. So the toxicity, when we refer to it in our context, it is above 10 parts per billion in water. Now, there are other regions that we have studied, and they contain extremely large concentrations, for example, greater than 1,000 ppb in Cambodia. So if we have all of these different concentration, now they all impact health, as I said. Now, surface water is less prone to arsenic contamination. That is why all these years, people have not been complaining about arsenic contamination just by water. Because on the surface, just like iron oxide, iron oxide is present on the surface. It is not, iron concentration is not there or not exceedingly large in water to cause significant impact on health. Now, arsenic concentration has not been significant for a long time. Now, in regions where there is groundwater is extracted, of course, there is excessive arsenic concentration. So there are reasons for this arsenic mobility, which people have studied. We will spend some time on this. So arsenic is present in the earth, yes, below the ground. How is it coming into water? Over several years of research, people have talked about two possible hypotheses. One is called the pyrite oxidation hypothesis. Another is called the oxyhydroxide reduction hypothesis. We'll briefly spend some time on this. Both of these are hypotheses, by the way, and not fully resolved as to what exists or what happens in a given environment. So in the pyrite oxidation hypothesis, arsenic exists in water because of a mineral called arsenopyrite. Arsenopyrite is similar to pyrite. Pyrite is FeS2. Instead of one S, that arsenic is present, let us say, then you have FeAsNO3. ASFES or ASFES. So this entity that is present in presence of oxygen and water, what happens is that pyrite eventually gets oxidized to a species called FeOOH, over which arsenic is bound. Now, FeOOH is called iron oxyhydroxide. So in this process, pyrite is getting oxidized, over which arsenic is bound. So imagine a situation when there is water present on some minerals and water goes off, let us say, by some means. And in presence of water and oxygen, if the pyrite gets oxidized to iron oxyhydroxide, over which arsenic is bound, this is constantly interacting with the environment. Imagine water is coming in and interacting with the surface. Arsenic gets into this water because originally this was the entity, but later this is the entity that you have. This is what is interacting with water, and its chemistry is very different from the parent material. So water gradually can contain arsenic. Imagine you have a pump now. You are pumping away this water. It contains arsenic. So this is the reason for arsenic dissolution in water and arsenic detection in water by one theory, that is pyrite oxidation. This, as you can see, this requires oxygen. So where is this oxygen coming from? Oxygen is coming by you drilling a pump or a borehole into this arsenic-containing mineral region. So you are the reason for arsenic to come into water. You meaning the anthropological activities. Now, you can also do this very same thing by natural processes, is by oxyhydroxide reduction hypothesis. This says that imagine you have this arsenic adsorbed onto the surface by whatever other means, we may not be this means, whatever is the means. Imagine there is biological activity around in that environment because of bacteria, because of organic matter, because of carbonic acid. You can make this arsenic into a reduced form of arsenic. This is this form. And in this process, what you have is oxyhydroxide is undergoing a reduction from its 3+ form to 2+ form. So there are some further details in this. These two mechanisms are being proposed. Sum and substance of this is that you don't have to have human intervention for releasing arsenic into water by this methodology. So both of these methodologies have been, or hypotheses have been proposed. You have arsenic present across the planet. So these are various concentrations of arsenic detected. This is real experimental data which people have measured. Now you can also do these kinds of measurements and use artificial intelligence to predict arsenic in other regions. So this is one such study. This is 2020. Using data from 200,000 data points, people have predicted the arsenic concentration across the planet. And these are regions with increasing arsenic concentrations with this gradient that you can see, the color scheme. Some years later, the very same authors have also predicted fluoride concentration With 400,000 data, they predicted the fluoride concentration across the planet. So very interesting that it is possible today. They say that it is possible to predict concentrations between, the data points are at a distance of just about 50 meters. So it is possible to predict concentration to a spatial accuracy of that kind today. So from all of these studies, from the biological impact of this arsenic, how it impacts and all, the various species that are formed, people have come up with a model like this. So this you will find in our review. So if you look at arsenic can be there by volcanic eruptions. And so obviously it goes into air. It can come through rain onto the surface of Earth. Arsenic can come through anthropological activities such as these. There can also be arsenic can come through pesticides, through fertilizers. Arsenic can come through bore wells. Quite a bit of chemistry happens in aquatic environment. Lots of different species can get formed. These are all different kinds of species that you see. They are labeled here. So inorganic, this entity that is there in the environment, but it can become this entity can become this entity with one methyl group added. It can have 2 methyl groups added. It can have 3 methyl groups added. It can have various other functionalization. So all of these are species of relevance. And all of these impact our environment. Arsenic 3 is more toxic. Arsenic 5 is less toxic. Several organic species are toxic at all because they get released through urine. So with that, we understand that there can be tremendous impact. So why is that impact? Because if you start thinking about the amount of arsenic in water, that's pretty large. So numbers are things like these. And these can get into phytoplanktons. Organisms accumulate. So in a given environment, if there is a greater release of arsenic, just as we saw in the context of mercury in Minamata, there's greater release, there can be greater impact in that environment. With that, we will take a few questions. And I would like Ramya to, first of all, I would like you to take this QR code onto your phone. And then Ramya will share the questions.
We'll have a few questions now and a few at the end of the class. The link would be the same. Okay. Shall we move on to the questions?
Yes.
Oops. Okay. Which arsenic species is typically more mobile and harder to remove by adsorption in groundwater? We have equal takers for arsenic 3 and 5.
Well, probably one aspect was not emphasized, that it is arsenic 3 is more mobile. What is harder to remove probably has to be inferred from that. Arsenic 5 is easier to remove. Arsenic 3 is harder to remove. That is the reason why it is existing. So the answer is arsenic 3. Okay.
Thank you, sir. With that, we'll move to the next question. Your sensor reads 9 parts per billion today, 12 parts per billion next week from the same tap. What's your first hypothesis? This is just some food for thought. Of course, all plausible need to replicate. We'll move on to the next question for want of time. Wow. Okay, I'll read the question. If a sensor detects 1 ppb arsenic, it is sensitive enough to check compliance with the 10 ppb guideline. True, I don't know, false. Engineers don't know, is it?
So a sensor is sensitive, okay? Sensor is good. Sensor has been sold by good people. Sensor is reliable. So if the sensor is reliable, then what happens? So if the sensor is 1 ppb, of course it is following, it is compliant. Water is compliant.
Okay, this is the last question now, and I'll hand it over to sir. If iron is also present in groundwater, which is the best pre-treatment idea to remove arsenic removal reliably, with high reliability? Yeah, oxidation and filtration. So with this, I stop and over to you. Thank you, students.
All right. We have not covered all of these topics in great detail, but we will come back to this in the course of time. So there are several environmentally relevant species. So we talked about a few of them. Now, you might be wondering, all these are present in water? Yes, of course. All of these can be present in water, depending upon the kind of environment. And depending upon the level of sensitivity that you have, many species can be present in water. But it is not that arsenic is always a toxin. It has uses. So one major use of arsenic is this particular compound, roxarson. Roxarson. It's called also ROX, and that is this species. This molecule is used as a growth enhancer in poultry and also animal feed. It has been banned in America, but it continues to be used in different parts of the world, including in India. So this is one use. Now, arsenic is also used across civilizations as a herbicide. It has also been used as a pesticide and all that, as I talked to. It's also used in leather finishing. But more recently, it is used in anti-cancer treatment for a particular kind of anti-cancer. So these are the two major things that we have. The uptake of arsenic, if arsenic is present in the soil, there can be many foodstuffs which can get contaminated. Yeah, several foodstuffs can have arsenic. One foodstuff which can have more arsenic is rice. And where exactly in rice? Mostly in the outer shell is called the aileron region of rice. So people clean rice to ensure that there is no arsenic that is there. People do, of course, washing and several other things to reduce arsenic contamination. As I just now mentioned, there have been extensive research on the type of treatment that one should have to reduce arsenic contamination. I would stop by briefly touching upon this aspect that arsenic toxicity is largely because arsenic can exist in different oxidation states, and several biomolecules, especially glutathione, can be involved in shuttling arsenic from one oxidation state to the other. And arsenic is also very close to phosphate. So the arsenate and phosphate are closely related, which means that arsenic can be existing in DNA instead of phosphate. So as you know, DNA has phosphate. So this can affect the biochemical cycle, the functions, all of these. And that leads to a disease called arsenicosis. It has several symptoms, and that is largely around hyperkeratosis. And upon prolonged exposure, you can even get cancer. And there are several such conditions that people across the world are affected with today. And that is the reason why arsenic has to be removed from water. With that, we will go to the next question and conclude this. Is 200 ppb dangerous? Yeah.
Actually, we'll not have much participants. It's the same link for those of you who are here.
Okay.
So with this, I'll move to the next question. Knowing that it is dangerous or not dangerous, to know that, what extra information do you need? Exposure and frequency, duration, age group, alternate water resources, measurement quality.
Alternate water sources.
Sources, yes. Okay, with this food for your thoughts, let's conclude today's session. If there are any questions, online participants and those of you in class, please raise your hand.
Okay, and would you like to play that video and then close it, or? Thank you.